Well, we had stopped at a stage where I said that in principle we could solve Newton's equation of motion, the second law of motion, for a given body by pointing out that starting with m dv over dt equal to f of t, if we manage to specify the force on this particle at every instant of time, then it followed that the position of this particle at any instant of time was equal to the initial position plus the initial velocity multiplied by time in this fashion, plus a complicated quantity which was 1 over m, an integral from 0 to t dt2 for want of a better symbol, integral 0 to t2 dt1 f of t1. So you first integrate this from 0 to t2 and then you integrate it as a function of t2 from 0 to t, and in principle this was your solution. Now where is the difficulty in this problem? The answer is that the specification of this force at every instant of time in some sense already presumes the solution of the problem, because most often what happens is that f is a function of r of t. In other words, the force on the particle will depend on where the particle is. The moment that happens, you realize that this is a useless kind of solution, because out here you are going to have an r dependence, but that is precisely what you are trying to find out here. So in that sense, being able to formally integrate Newton's equation of motion is essentially useless, except in very simple cases, except if this were not true. If this were a constant force, for instance, or a force which does not have any r dependence at all but can be prescribed explicitly as a function of time, then of course in principle one can go ahead with this program and write down what the solution is at all instants, but otherwise it is not going to work. And now let me give you an example of a case where it does work, namely projectile motion. This is a classic example which you have already studied in some other context in a simpler notation, but we are trying to do this in the context of vector notation. So here we are. The problem is that if you take a particle and you project it at some angle to the horizontal and call this x and the vertical coordinate y, and the particle is under the action of gravity at every instant of time, then we are able to write down, if you project from the origin for example, r of 0 would be 0, one can write down what r of t is at any instant of time. So the idea is that the force of gravity on this particle is such that the f at all instants of time is minus mg times e subscript y, and that is independent of time. It is independent of position as well. There is of course a big approximation here. The approximation is that every instant of time the force is vertically downwards, and it is exactly the mass times the acceleration due to gravity. This would not be true if it were a projectile which actually went some distance, like a missile for example. In that case you start with the surface of the earth, you project from a certain point a missile, you launch it and it goes and lands somewhere else in this fashion. As you know, this is really part of an elliptic orbit if you neglect air resistance and you assume that this is essentially in free fall, then this orbit here hits it at this point, and clearly the force of gravity on this object is not constant at all times, because now you have reached a height which is comparable to the radius of the earth, and you have gone a range which is also comparable to the radius of the earth, and no longer do you have this approximation possible that the force of gravity is a constant independent of the location of the body and of time. Not true. But otherwise, if this distance here is extremely small and the height here is extremely small compared to the radius of the earth, this picture is valid approximately, and you have what is called a parabolic orbit. Technically this parabolic orbit is valid only if the force is a constant independent of the location and of time, but in practice the force of gravity is not directed with parallel lines of force, but rather they converge to the center of the earth, and then you got to do a more sophisticated calculation in that case. But here in this approximation that the force of gravity is a constant, the problem is solvable immediately. We could either write down the solution by plugging it into this thing here, or we could work it out laboriously one way or the other. So, r of t in this case is equal to whatever be the initial velocity out here, the initial projection velocity v of 0 t, which I believe is generally called ut, u times t, u being a constant. So, this is u times t plus 1 over m f of t, but f of t is a constant, it is minus mg. So, that portion comes out. Okay. So, this is equal to minus, and the m cancels out, the g comes out altogether, and you have an integral, and the e sub y comes out also, and you have an integral 0 to t dt2, 0 to t2 dt1 times 1, and that is it. And of course, this integral is simple, it is equal to ut minus g e sub y. The first integral gives you a t2, and integrating t2 from 0 to t is half t2 squared, and then half t squared if you substitute whatever is there, and that is it. So, that is the solution, that is the explicit solution. And just to keep track of things, let me call this v of 0, let me leave it as v of 0, so that it is explicit that it is the initial velocity. Assuming you project it from the origin, otherwise you add the position vector of the origin to this result here. Now, of course, the familiar formulas which you normally are used to for projectile motion emerge immediately from this. If you write it in components, it immediately means in Cartesian components, if x is the horizontal component, x of t is equal to Vx times t at time 0 times t, and the horizontal component does not change at all of the velocity, simply because there is acceleration due to gravity is vertically downwards and does not affect the horizontal component of the velocity at any time. So, it is Vx 0 of t out here minus, and this is in the y direction, and that is it, this is all it is. So, the horizontal component increases linearly with time if the velocity has an initial horizontal component. The vertical component is another story, the vertical component is equal to Vy of 0 times t minus half gt squared. And this is the expression that you plot x versus y will give you a parabola, because this goes linearly with t, this goes quadratically with t, and when you eliminate one versus the other, when you eliminate time between these two quantities, these two variables, then you get a parabola in the xy plane, and that is the path of the particle, the trajectory that you get. Now, we were able to integrate the equation of motion in this case explicitly because this force was a constant force, and these integrals could therefore be done immediately. But in the non-trivial cases where it is a function of the coordinates in general, this would be a much harder problem to do. So, this is not the way to do it, straightforward integration generally will not work, and that is important to understand. It is also important to understand the role of initial conditions, and let me say a word about this here. If I start with this object here and I say there is a force of gravity acting on it and nothing else acting on it, I tell you what its initial position vector is, and I tell you the force on it initially and at all instants of time. It is not possible to predict the future path of this particle based on this data. The reason is, if I let go from rest, it will fall straight down towards the center of the earth, but if I give it a horizontal velocity initially, then it moves in a parabolic path and falls in a trajectory like a projectile. I give it a slightly higher initial horizontal velocity, it goes further, the range increases. In principle, if I give it a high enough initial velocity and there is no air resistance, it would go into an elliptic orbit around the earth. And in principle, if I increase the horizontal velocity further, it would go into a hyperbolic orbit and escape the earth's gravitational field altogether. So, it is clear that specifying the instantaneous position and the instantaneous force on it is not sufficient to solve for the particle's trajectory at all subsequent times. That is what we are seeing when we see that this displacement or position vector at any time is dependent on the initial position and the initial velocity. So the initial conditions matter. Not only does the initial position matter, but the initial velocity also matters. That is telling us something extremely deep. It is telling us that when you solve an equation of this kind, or you rewrite this in terms of the position, you write this as m times d2r dt2 f of t, you have two constants of the motion, so to speak, two vector constants of the motion to deal with, namely the initial position and the initial velocity, before you get a unique solution for the position of the particle at any instant of time greater than 0. And those initial conditions are the initial position and the initial velocity. It is not enough to specify just this or just this, you have to specify both. And when you have more than one particle, you have to specify in principle the initial positions and the initial velocities of all the particles before you can find a unique solution for their paths in time as a function of time. This has to be appreciated carefully, and it is a consequence of the fact that Newton's law says that the force on a particle changes its velocity and therefore its position as a consequence, and does not directly become proportional to the instantaneous velocity of the particle. It is proportional to the instantaneous acceleration of the particle. This is important, very, very important. It took a long time to understand this this fact of nature, so to speak, and it has got important consequences. It essentially says that what varies as a function of time, what dynamics is trying to tell you, is how the positions and velocities of various particles change as a function of time, or more generally the positions and the momenta of these particles, of these objects, change as a function of time. We will come back to this idea. So that has to do with the importance of initial conditions. We are going to say a lot more about initial conditions as we go along. Meanwhile, one small digression. We should have done this a little earlier, and that has to do with the so called work energy theorem. Let us go back to this equation and look at what it has to say. So if I take a single object, a mass m, and apply a force F on it, which could be time dependent, then I get an equation. Newton's equation says that m dv over dt is f of t. Now let us take a dot product of both sides of this equation with v itself. Suppressing the t dependence in all these quantities, this is what this looks like after I take a dot product on both sides. Now what is this thing trying to tell you? You have a vector dotted with the rate of change of that same vector, and there is no reason to imagine that this is normal to that or parallel to that. These two could be in very different directions. We already saw that in the case of motion in a circle. We saw that in general the motion in a circle was such that there was both a tangential acceleration as well as a radial acceleration. So that tells you that although the velocity is purely tangential in the case of motion on a circle, the acceleration could be radial, normal to it, could be partially tangential, partially radial. No general principle at all, no general constraint at all. In general, these vectors are not either parallel or perpendicular to each other, so this dot product has some value of some kind here. But there is a simple identity one can write down. If you give me any vector u and you write it in Cartesian components as u, y, u, z, then u dot du over dt, if u is a function of time, in other words its components change with time, then if I write this out in Cartesian components, this is ux ex plus uy ey plus uz ez, and that is multiplied or dotted with dux over dx ex plus over dt, duy over dt ey plus duz over dt z. Ex dot ex is 1, and Ex dot Ey is 0 and Ex dot Ez is 0 because these are perpendicular vectors. Therefore, this thing becomes Ux dux over dt plus Uy duy over dt plus uz over dt. It's identically equal to that. But ux dux over dt is half of d over dt ux squared. So you can write this as equal to 1/2 of d over dt ux squared plus uy squared plus uz squared. But ux squared plus uy squared plus uz squared is equal to 1/2 d over dt of u squared, where u squared is the square of the magnitude of this vector. But that of course is equal to 1/2 times 2 times u du over dt, and the 2 cancels out and we are left with this identity which says that for any vector u which depends on time, u dot du over dt equal to u magnitude d over dt the magnitude. This is identically true. These vectors can point in arbitrary directions, but the dot product of the two is just the magnitude of the vector times the rate of change of the magnitude of the vector. Okay. That is an extremely useful identity which is used over and over again. It is a very simple identity, but you see what happens here. Once I use that identity, the left hand side becomes mv dv over dt. No vectors, and that is equal to f dot dr over dt, because the velocity is dr over dt. Okay. And now I move dt to the other side and integrate, so I get mv dv equal to f dot dr, and I integrate both sides, and let us suppose I start from 0 velocity, 0 speed, and integrate up to some speed, the object attaining some speed, then 0 up to v prime dv prime is equal to the integral on the right hand side starting from wherever the initial value r is up to wherever it ends at when the velocity is v, wherever. But this right hand side, so there are limits placed here. But the right hand side f dot dr, we know that if at any instant of time the position vector of this particle is r and you apply a force on it and it causes a displacement dr, then f dot dr is the work done on this particle by this in this infinitesimal displacement by the force. So this is equal to work done on the particle, on the object, to do what? To start it at rest and give it a velocity v, a speed v, and this side is trivial to integrate. This is half mv squared. So it is the work done on the object to change its speed from 0 to v. But that is called the kinetic energy of the body. So we have a definition of the kinetic energy. This is the so called work energy theorem, quote unquote, because it is just a straightforward consequence of Newton's equation here. It says the work done in moving an object from rest to some speed to give it some speed v is called the kinetic energy of this object, and it happens to be half mv squared here in this sense. A little later we will see, when I talk about relativity, we will see that this formula is an approximation, just as Newton's equation itself is an approximation when the speeds are very small compared to the speed of light, and moreover when you are in an inertial frame. So we will come to these things a little later, but right now I just wanted to point out that here is an operational definition of the kinetic energy, and this is how the formula half mv squared arises by this simple argument here. Okay. Now a couple of questions. One of them is the following. Newton's first law told us that an object either continues to be at rest or moves in a uniform in a straight line with uniform velocity if there is no external force on it. The second law on the other hand says that the mass times the acceleration equal to the force on it. Now if the force on the body happens to be 0, then it says the acceleration of the body is 0, which says the velocity is a constant. So if f equal to 0, then v of t is equal to v of 0. Whatever was the initial velocity will persist for all time if the force happens to be identically 0 at all times. But that is the first law. So does this mean that the first law of Newton's laws of motion, the first of the laws, is not independent of the second law? Does it mean that it is derived from the second law? It would look like it. It would look like saying that the first law is a special case of the second law when the force on the body happens to vanish. Is this true? It cannot be, because we have three laws of motion and they have to be mutually consistent with each other, and I leave it to you to think about this, and we will talk about this a little later as to where the difference between the first and second laws comes. So it is not that the first law is a special case of the second law. It is true that the laws are consistent with each other, they have to be, otherwise they won't form a set of laws of motion, but it is not true to imagine that the first law of Newton is actually derived as a special case of the second law. Not true. Think about why this should be so. Alright, now that we have gone this far, let us go back once again and explore where these laws, what these laws are really trying to tell us. Well, I mentioned a little bit about the importance of initial conditions, but we need a little more than that. In principle, when we are trying to integrate equations of motion, there are constants of the motion, integration constants. Now in the mathematical sense there may be integration constants, in the physical sense they are initial conditions. So you need to know what the initial velocity is, what the initial velocity of each particle is or each object is, the initial position of each object is, and you need to know the set of these conditions for all the objects that you deal with in your dynamics problem. Okay. How does one discover these constants of the motion? Well, either you specify all these initial values or you specify quantities which do not change with time, and already the first law is trying to tell you something about it. It is saying that if you do not have any force on an object, by the way, just one small remark, it is a very important one though, this quantity here is not the most general form of Newton's second law of motion. The general form is that the force is equal to the rate of change of the momentum of this body, and the momentum is defined as the mass times the velocity at this level. Now this might look like a very trivial statement. This might appear that all we have done is to take this m inside, and since m is constant, whether we differentiate with respect differentiate p or v does not matter. Not so. Not so at all. Even if m changes with time, this is the correct law and not this. That is the first point, that this is the right law. The second point, which is even more profound, is that the momentum is not always defined as the mass times the velocity. We will come to examples of why this is not so, and there are fairly simple examples of why this is not so. The momentum has a slightly more general definition than the mass times the velocity. In the Newtonian approximation that we are dealing with here, implicitly the mass times the velocity of an object is indeed its linear momentum, but this is not the general formula. And the fact that this is the rule, the law of motion, and not this, is actually dramatically manifested in the case of say a rocket, which is carrying its own fuel, and as it goes up in its path the mass is changing because the fuel is burnt. and put out as gases, exhaust gases, in which case this is the correct law. So if you give me the instantaneous force on the rocket, I can tell you its rate of change of momentum, including the fact that its mass is changing as a function of time. So this is the right law here. We will keep this, and we will use this only in those cases where we are very sure that the physical situation is such that the mass is a constant and you are in the regime in which this law is applicable. We will be careful about that. Okay. Now the first law essentially is telling you that in the absence of an external force, the momentum does not change. In other words, the momentum is constant. So it is really telling you, the first law, P is a constant of the motion and I am going to use an abbreviation COM for it because it is so important as a concept. P is a constant of the motion when F is absent. If there is no force on a body, then according to Newton's first law, its momentum is constant in time. That means it is constant not only in magnitude but also in direction. If it started out with 0 momentum, it remains at 0 momentum, it remains at rest. If it started out with the finite momentum in some direction, then the momentum continues to be the same in magnitude and direction as a function of time. For all time it remains so, and therefore P is a constant of the motion, actually a vector constant of the motion. So there are 3 components here, each of which is constant in time. So there is a deep symmetry principle involved here. We will talk about why these constants of the motion arise. Where do constants of the motion arise from? Why are certain combinations of these dynamical variables constant in time? This is very deep in dynamics itself. It has to do with the symmetries in the problem. Just to cut a long story short, and we will talk about this, elaborate on this, momentum conservation arises because of the homogeneity of space. When space is assumed to be homogeneous and there is no difference in space between one point and another, then you have the possibility of the conservation of momentum. Similarly, the conservation of energy comes because of the homogeneity in time. If you say that the origin in time is irrelevant, the law does not change. If you start the clock at different instants of time, then you have the possibility of the conservation of energy. And the conservation of angular momentum also has a geometrical or a physical explanation. It arises because space is isotropic in all dimensions. In other words, in all directions, if space is exactly the same properties, then you have the possibility of angular momentum conservation. When these quantities are not conserved, then there is some physical effect which is spoiling the symmetry, which is breaking this symmetry, and that is what is responsible for the conservation law to break down. I will elaborate on this starting with the example of the projectile itself. It will be easy to see where this comes from and what these constants of the motion mean. And this is a very, very basic and important concept in dynamics, and if you understand what the role of constants of motion is and what the role of symmetries is in dynamics, then you have gone a long way in understanding the structure of Newton's equations and their solutions in specific cases.